Okay, so the first question was given a nomenclature problem with R and S in the name, and then given 2 carbons of a sigma bond, how would you choose the correct Newman projection corresponding to that structure? So let's start with say S 2-chlorohexane. So if you were given just this name, the first thing that I would do is write out the longest chain, then at the 2 position put a chlorine, then figure out whether the chlorine should be a wedge or a dash, and then from there we'll look down a certain bond and then determine how to draw that. So we'll sort of take it stepwise to cover a lot of different concepts. Okay, so the first thing I would do to convert this, even if the exam has A, B, C, and D, which are Newman projections, you probably want to draw it out sort of flat first, just so you get an idea of how it looks. So we have 1, 2, 3, 4, 5, 6. There's the hexane. The chlorine is at the 2 position, and so what we need to do now is determine whether that C-Cl bond is a wedge or a dash. So we want basically, if we make it, let me ask you a question. If we make it a wedge, what would the stereochemistry be? So it would be R. So we have to depict it as a dash then. So again, I'm a fan of doing things incrementally like that. That way you sort of see how it builds up. Then let me throw the numbering in there. If you were asked to look down, you know, the 2-3 bond that way, or if one of the answers was presented that way, again, drawing it out like this first would help you a lot. So one thing to help you draw this Newman projection, the carbon at 1 is down, so it's going to look like the front carbons at 2, which we're looking at, is going to look like a regular Y. So this is carbon 1 right there. So off to the left of that Y, what substituent should I draw there? So the chlorine, so Cl, and then this is the H. So hopefully you can sort of see that. And then the circle is the back carbon, and the way that this is drawn, the chain after it is anti. So the thing that is up is the rest of the chain. So we're looking down the 2, 3, and then everything else would be 4, 5, 6. So 1, 2, 3, 4, 5, 6. So that should be the right number of carbons there. So again, a Newman projection looks down the axis of a CC bond, and so if you count from 1, you have 2, 3, 4, 5, 6. So if you were given the Newman projection and asked to figure out the name, we'll do one of those. I'll try to make it a little complex so you can see sort of the route you have to follow to figure out what the chain is. But yeah, determining, I would draw things flat and then convert it. Whatever you do, if you have to make comparisons, make sure you're comparing Newman to Newman or flat to flat. When you go between the two, that's really hard to compare.
When you are doing like the RNS and trying to figure out like when you try to do the chlorine and ash and the wedge, would you always just kind of like try to assume it's the wedge first and then try to do it like go from there, or?
Well, maybe let's do S2-chlorohexane and see what that would end up being. Or sorry, S3-chloro. So for this one, now the chlorine is on a carbon pointing down. And so do we need that CCl bond to be, at this point, a wedge or a dash? I think it's going to be a wedge. So let's redraw that in that form and see what happens. So we're going counterclockwise, so that should be the S. I would say the best strategy overall is to draw things out. Again, if you can draw it out, then figure it out, that's fine. If not, definitely resort to the models. Because yeah.
So how do you know if it's going to be dash or wedge?
Like, other than like drawing it out, like how am I thinking about it?
Right.
I've sort of done enough of these that I can compare if I do it both, what it's going to be in my mind, but I would say draw out both is the way to get it right. So let me draw a more complex molecule in a Newman, and then we'll convert that Newman to a name. So I'm just pulling problems out of your textbook, chapter 4 at this point. So there it is. Maybe a strategy you can take is, again, you're looking down carbon-carbon. So that's 2. The front carbon only has one chain coming off it, so that has to be included. So what I'm going to do here, just in like green numbers, is like maybe temporary. I'm going to say 1, 2, 3. Then we're looking down 4 to 5. So the back carbon has 2 chains. So if I go down this way, it's 6, 7. If I go the other way, it's 6, 7, 8. So that's the chain that we would have to count. And then the stuff that's off that chain are substituents. So 8 carbons is what parent? And then we have substituents off which carbons? So what's on carbon 5? And then what's off carbon 6? So then we're going to lump that together alphabetically. So ethyl and methyl. Five ethyl, 6 methyl octane. You are looking down the 4 and 5 of the Newman. So really that's the focal point in determining the name from a Newman projection. So the first carbon only had one carbon chain coming off it. So that was, you didn't have to choose anything there. But the second carbon behind it had 2, so you had to count both, and then whichever one's greatest is the parent. Maybe I'll throw another one like that in there. Okay, so here's a doozy. So what would you name that? So the front carbon and the back carbon are connected to one another. What does that mean? So what size ring is it? It's 5. So it's a cyclopentane. So the one, or the front and the back carbons both have substituents. So if we call the front carbon 1 and the back carbon 2, what would the full name of this compound be? So 1,2-dimethyl cyclopentane. That's almost there, but not quite. So we need something else. What's the relationship between the two methyl groups? What? No. You could use the word anti, but in this scenario it would be trans. So it would be trans 1,2-dimethylcyclopentane. So that would go in front of that. So what would it look like if we put that in flatland? So say this was the first carbon, and then the back carbon would be that. So just to refresh your memory, how many unique carbon signals would this molecule have? What'd you say? It'd be 4. The reason it's 4 is because this molecule has a rotational axis. So you can spin that, and those methyl groups essentially are the same thing. So 180-degree rotational axis is called C2 symmetry, and that ends up being pretty important in nature. Let me ask one more question with that. In the proton NMR, that methyl group would occur as what type of multiplicity? How many neighbors does it have? What'd you say? It has one neighbor, so it would be a doublet. Let me draw up another Newman, and we'll go a little bit deeper down the rabbit hole here. So what's the name of this compound? Say it again. No, what'd you say? So now you're looking down what I call a double-barreled Newman. Each Newman has 2 carbons, right? Then each Newman is connected by a carbon, so that's 2 more. So what size ring is it? It's 6. Isn't that what you said? You always got to trust your gut instinct. There's like a thought process. Like as soon as your eyes like track something and you get that thought, that's what you should go with. You know what I mean? But sometimes that doesn't work. So it's a 6-membered ring. It's a cyclohexane. Let's like sort of go through this stepwise so we don't bunch too much together at once. What substituents do you see on there? So now you have a polyfunctional molecule. The alcohol gets the priority. So it's going to be a cyclohexanol. Now we have a chlorine and a methyl. So chlorine becomes chloro, methyl is methyl, and now we just have to figure out the numbering. What's the numbering of each substituent? What? The alcohol's 1, and then what do we want? What's the methyl group going to be numbered? It's 2. So it's on the carbon right behind the alcohol. So that's 2-methyl. And then the chlorine should be what? So 5-chloro. So we're going to put that in order of alphabet. So 5-chloro, 2-methyl, cyclohexanol. So this page is getting a little bit busy, but we have still a little bit of white space. Let's take that Newman and put it into a flat cyclohexane, and then you'll tell me whether things are wedges or dashes. So I've put some numbering in there. Carbon 1, we said, is bearing the alcohol. Is the alcohol then a wedge or a dash? It's a wedge. How do we know? So I guess from my bias, the way I do this is, so we're looking down a Newman, so I'm sort of going up and then looking back down on the top face. So my eye is here. If my eye was the other way, it would be a dash. But the important thing for now is that we get the relationships between all the substituents right. If the alcohol is up, the methyl group should be what? Should be a wedge or a dash? What? Should be a wedge. See how the alcohol is up and that methyl group is up? So they are on the same face. So if we're drawing that alcohol up, the methyl group also has to be up. So at the 5 position, looking at the relationship between the alcohol and the chlorine should be what? Should be a dash. maybe I'm gonna move on to a clean slate here. Next question.
Can we go over some like acidity and like just a refresher on that? Like assigning acidity to the function?
Yeah. So I've explicitly labeled 4 hydrogens here. So they all have 4 different pKa's because they all belong to different functional groups. So you'll be given a pKa table on the exam, so you don't have to memorize the numbers. But what you do have to know is how a general functional group is represented on that column or however it's presented to you. If you don't know how to like sort of navigate the data, it's it's not even worth having. So the skill is knowing why that functional group has that acidity. So here we have an alcohol, and what would you say the pKa of that type of alcohol is? No. Do what? So this one is in the middle. It's 10. This type of alcohol, which is bonded to an aromatic ring, is about 10. So below there, right here, we have an sp2 hybridized carbon bonded to an H. Where does that acidity fall into? Huh? 50 or 15? I don't think it's that high. So when you change the hybridization, you lower it a bit. So on the table there, do you see ethylene? So at the very bottom it's ethane. What's ethylene? It's 44, okay. So I'm just going to call that alkene. So now the next one is an sp3 hybridized carbon CH bond. But what is unique about this is it is alpha to a carbonyl. So it's not alkane acidity. It drops it quite a bit. So this one's going to be about 25. And then finally, the carboxylic acid is what? About 5. So again, remember from the beginning of the semester when you were asked, determine the unique, or determine the total number of sets of unique hydrogens. You were doing it in terms of the context of NMR, like how many signals you would see. That also applies to this because each set belongs to a functional group, and each functional group has its own acidity. So if we treated this compound with one equivalent of any base, the lowest number gets deprotonated first. So let's draw what that looks like. The base that we can use is pretty common, sodium hydroxide. So there are the verb meanings of acid-base. They always occur in a pair. You always have an acid-base reaction. The base abstracts the proton, the acid donates it, so it's a relationship. So the arrow starts at the place where there's the most electron density, and that's the hydroxide. And so it's coming over. So this arrow means that that oxygen is forming a bond to that hydrogen. Hydrogen can only have one valence at a time, so we're breaking this bond. So notice the arrow flows like head to tail. The two heads never point at each other. They never like point away from each other. It's a flow. So once that happens, we get water as a byproduct. So that is the conjugate acid of sodium hydroxide. Now this oxygen has the negative charge with the sodium counterion. So it's important that you always balance your charges. We start neutral, we end neutral. Charges are neither created nor destroyed. You always want to balance them out. Anion is balanced with cation. So again, what we're going to start learning in a couple weeks, you know, an acid-base reaction. Now that is going to be a tool for making other things. So we went from an OH bond, say we want to make an O carbon bond. So that's what you're going to be learning in the substitution chapter. You had a question?
Did you say to draw the H at the bottom? On the ring?
Yeah, I just didn't put it in. It's still there.
And the equilibrium lies to the right because the volume is viewing for absence.
Yeah, so this is the number we're concerned with here. The number we're concerned with here is of the water, which is 16. So that's why I drew this arrow just one way. So that's irreversible. And this is what I find sort of, I don't know, complicated. This is an equilibrium. The equilibrium lies 100% to the product. So that's, and so the reason it does that is based on the energy surface. It's under those conditions, once you hit the top of the hill, you slide all the way down and you can't go back up, so to speak. Let me go to the acids chapter and pull out some more. So there's a question 341 where they give you a reactive intermediate and they're saying, what is the reaction with water? So maybe we can try that based on what we know. So the thing to the left is a ketone where one of the lone pairs on the oxygen carbonyl has been protonated. that is reacting with water. And what we want to show is a proton transfer. So the thing on the left is the acid, the water is the base. So again, in terms of metacognition, these things right here, acid, base, need to be at the forefront of your mind when you're drawing these arrows. We'll do it right the first time, and then I'll show you some very common mistakes the second time. So let me say, this is the acid, this is the base. The base is abstracting the proton. The oxygen is plus. That oxygen wants to be neutral, so it needs another lone pair. So this lone pair here is going to abstract that. That bond then breaks. The electrons go on. The oxygen of the carbonyl. So we end up with the ketone, which is acetone and a hydronium ion. Does your table have, I know your table has the hydronium ion pKa, but does it have a protonated carbonyl that you can see? If you have this one, it's on this one. It's at the very top. To the right-hand side, the first box. So the initial starting acid, that pKa is minus 7.3. So again, if we're shifting the equilibrium towards the weaker acid-base pair, it's gonna lie towards the products, but we could still draw sort of a tiny arrow going back this way. How many people plan on taking biochemistry? So quite a few of you. The stuff that's going on in your body right now, biochemically, is what's happening here. They call it proton transfer. It's going from one site to another. And the reason it does that is to activate the molecule for a reaction to occur. Proton transfers are diffusion controlled in terms of kinetics, and that just means they happen super fast. So maybe let me redraw this, and I'll show you some stuff you don't want to do. And hopefully you'll see why you don't want to do that, because it violates stuff that you already know. Like, you shouldn't speed through a red light. You might get T-boned. One thing that a lot of students will do is sort of reverse the arrow flow. So you saw initially we had to use 2 arrows. A lot of students will just start the arrow here and just use like 1 arrow to move that proton. So the reason that's wrong is because in the product you're ending up with the following. If you're keeping track of your lone pairs. Does everyone see why that's wrong? Huh?
But it's the
Yeah, it violates the octet rule. So the ketone ends up with, it's shorted an electron pair, and then this other oxygen that has 3 hydrogens has 2 electron pairs and 3 bonds to hydrogen. And so your eyes do not deceive you. That is not right. So you really need to, as a student, just have confidence in what you've learned so far and say, this does not match what I normally think it should be, so it has to be wrong.
Can you explain like what the error like this low electron means, like how we supposed to see that? I guess.
So maybe I'll So here's 2 compounds. One you're given a Fisher projection, the other you're given a Newman projection. And basically the question is asking, would either of these compounds be optically active at room temperature? So the one that's presented as a Fisher projection, would you expect that to rotate plane polarized light? You say yes? So the molecule does have stereogenic carbons, and I'll put asterisks by them. So those are 3 stereogenic carbons. So stereogenic carbon can have R or S. We have 3 of them, so 2 to the 3 is 8. But it's asking about this one in particular. If I told you the answer for this one was it is not optically active, what reason would you state why? What? It has an internal plane of symmetry. Do you know what that's called? It's meso. So it's sort of different from the meso one we saw in class today. The internal plane in this compound, it bisects here. So when we saw it in class today, it actually bisected between the carbon-carbon bond. This is bisecting right through the atoms themselves. So that one will not rotate plane polarized light. What about the one that looks like a Newman? Will that rotate plane polarized light? So what's challenging about this one is the methyl groups are anti. So you really need to put them in the eclipsed form to determine if there's an internal mirror plane. So let's go ahead and do that. So this arrow with the little loop means I'm going to do a rotation. And what I want to do, I'm going to keep the back one the same and rotate the front. So that one, once you do that rotation, now you can see that those substituents mirror each other when they're eclipsing. And so if I were to convert that into a Fisher projection, it would look like this. What should go on the left here? So now you can see that this plane bisects the actual bond itself. So meso has stereogenic carbons, but has an internal mirror plane. All right, I got a nice one. Nice. It's real nice. So this is problem 560 from your textbook. It says, draw a Fisher projection for each of the following compounds, placing the acid group at the top. I know we didn't cover Fisher projections a lot today, but in a Fisher projection, the way it's defined, the most oxidized carbon is always at the top. And so that is the acid. So what do they want us to do? Or as my dad says, what are we going to did? So there's the acid. The first sort of horizontal line isn't too bad if you consider the following. I'm going to put that H in there. Now your eyeball is right here. So there's your eyeball. And you're looking at that bond. So where I've drawn the intersection at carbon 2, what should go on the left side of that bond? So the OH. Then the H goes on the right. Now this is where you don't want to get fooled. So anyone listen to The Who? We won't be fooled again. So I would say expand your musical horizons if you can. You'll enjoy it. It's a good album. So what I'm going to point out here, so 1, 2, 3, and 4 are anti. In the Fisher projection, we need them to be eclipsed. So what I'm going to do is a rotation about the 2 and 3 bond. So you got to do a rotation. So this is carbon 3 now. Carbon 4 is not a stereogenic carbon, so I can just do that. So without me actually drawing the rotation, at carbon 3, what should go on the left? What? I believe it should be the H. And the right should be the OH. You're asking, how do you know that without referring to a model? See how the OHs are now, like cis to one another in a sense? When you do a rotation and you keep that 3-4 bond in the plane, so it is eclipsing the 1-2 bond, the OH groups are then going to be anti to one another, or cis to one another. Or wait, no, trans to one another. Sorry, I'm confusing myself. They're syn now, they're going to be anti when you do the rotation. Can you envision doing that in your head? I'll make a model right here. So let me pause there. So this is question 575, and it's asking, what is the relationship between these two molecules? Anyone have a guess? It is not flipped. Let me ask you another question that'll sort of maybe lead in. How many stereogenic carbons do you see? What'd you say? There's 3. Does everyone see where they are? So if I put these hydrogens in, so where those two rings meet, those are stereogenic carbons. You can overlap them, and the ring ones will be the same. So maybe I'll just draw those in blue. Then the ones in red are different. So if you have 2 the same and 1 different, what's the relationship? What? They're diastereomers. Yeah.
So on the best, like with the chairs, what are you gonna like specifically ask us? Like, are we gonna need to be able to know?
Yeah, let's I guess look at that. So I'll call this so cyclic conformational analysis. So there's the flat cyclohexane, then I've drawn the chair and I've numbered it. So the alcohol is at position 1. At carbon 1 in the chair, how should I draw the OH group? Would it be equatorial or axial? Be what?
No, axial.
It'll be axial. So carbon 2, the methyl group should be what? Equatorial. So if I draw a ring flip, so everyone sees how the numbering changed. Well, not changed, but carbon 2 goes up, carbon 5 goes down. So there's like a shift in how the numbering looks. So then the OH group at 1 should be in what position now? So equatorial. Then the methyl group at 2 is going to be axial. So to get to answering your question in terms of the broadest sense, if you were given like a flat cyclohexane, and then a question could be of the choices A, B, C, or D, which one represents that as a chair? Or if you were given a chair, which choice A, B, C, or D represents the proper chair flip? So there's not many tricks I can pull out of my hat to make those answers wrong. Either the relationship between the substituents isn't the right 1, 2, or 1, 3, or whatever, or the cis trans is flipped. Really, I think if you understand the logic, it's just about paying attention to what the answer choices are. Yeah.
Will there be any questions like which one is more favorable? Which one is naturally?
So there's probably going to be something like that in some flavor. It'll probably be obvious about what it is, because again, you only know so much, and I don't expect you to know like an advanced level of things. So again, I have to spice up the question somehow. Yeah.
So, did you know that one, the first one, the OH was axial just because you started with it, or how do you know that one?
So let's do another one, and I'll sort of explain how we're getting to that. Try to find one out of the book here. So this is just a practice problem from chapter 4, page 176. So we have a chlorine, a methyl, and an ethyl group. So this first chair that I'm going to draw is going to look like this. And really, there's nothing magical about this. What you just have to realize is whether the carbon in the chair is up or down, and I'll explain that as well. So I'm going to go ahead and arbitrarily throw some numbers in here. So say I'm going to call this 1, 2, 3, 4, 5, 6. Again, you just need to be consistent about like how you're going from one to the other with any potential numbering. So I'm going to say that the odds 1, 3, and 5 are up. The evens 2, 4, and 6 are down. Because carbon 1 is up, the up bond is going to be what? It's going to be axial. So therefore, the ethyl group is up. Carbon 2 is down. So the up bond on carbon 2 is going to be what? Equatorial. Because they have to be on the same face, because we know that we see that there's cis there. Carbon 4, the chlorine is down relative to the two other substituents. Carbon 4 is down, so the down bond must be what? Axial. So let me draw the chair a different way and put the numbering in a different way. So now I have the 1, 3, and 5 are down, the 2, 4, and 6 are up. So the up bond of carbon 1 is what? So equatorial, so that's the ethyl. The up bond of carbon 2 should be what? So axial. So see how they're now still cis to one another. And then the down bond of carbon 4 should be what? Equatorial. So what's the relationship now between those two? They're the same molecule, but they're conformers of one another. So the difference between them is what? So it's a chair flip. So the things that were axial become equatorial. The equatorial become axial. So I didn't draw it like a normal chair flip like you would see 1 going down and 4 going up, but just the fact that I sort of renumbered and it's a chair flip but looking at it from a different perspective.